In that case, we can move on to image synthesis. This one I covered last year, so I'm not going to spend too much time on it. The video is online. And it's the same idea as before. You have a framework, you worked on it for a very long time, you show it to your customers, and then your customers are not going to be happy. And what is the framework? It's the Pix2Pix framework, where you had a semantic map, and then you were mapping it to generate high quality images. And these are going to end up being the type of images that you're going to get in the end. This is not Pix2Pix, but it's a modification on Pix2Pix to make it even better. And these are the results of this paper. So they are starting to look much better. And what are the applications? Why would you try to have a semantic map? Because you can actually start changing the semantics of your input. For instance, you can change these trees, and all you need to change is the corresponding one-hot vector. Make that one-hot vector be one at a different location. And then you can change your trees to buildings, or you can change the paving of a street, or you can change how the objects are going to appear. And this way you're augmenting your data set for your self-driving car applications or for your video gaming applications. So Pix2Pix, you had a generator, you had a discriminator, you were conditioning on the semantic label maps, you had your GAN loss, the network structure was type of a unit structure where you have short connections or shortcut connections. And then your discriminator is going to focus on patches of your images. So you have a discriminator looking at this part, and then your discriminators are going to look at patches of your images. And then after all of that trouble, you were able to generate 256 by 256 images in terms of resolution. Now you want to increase the resolution to be high definition. You need to first modify your architecture a little bit, and this is how you're going to change it. Your architecture is going to have two steps. In the middle step, you are going to be working with low resolution image. So basically downsample these guys. And that's the resolution that you're going to be training your neural network on. And then you're going to have some additional layers, which are going to work with higher resolution. The higher resolution, you first featureize it so that the feature map has the same size as the feature map from the smaller network. And then you add them, and then these are going to be the inputs to your decoder, which is going to output images. And it's going to end up being a two-stage training process. You first train this guy on lower resolution images, and then you train these additional layers. So it's a middle step between progressive growing and having a single neural network for everything. So now you're progressively growing in only two steps. You're going to have a multi-scale discriminator. You improve your adversarial loss, and then that's going to give you your generator loss function. And your discriminators, you're going to have three of them, which are going to not only operate patch-wise, but are also going to operate at lower resolution or at multiple resolution. If you have a patch here, your discriminator is you're going to have three discriminators, and then each one is going to look at different resolutions of this image. And why is that? Because the ones that are working with lower resolution version of this patch are going to see the big picture, and the ones that are focusing on higher resolution are going to look at fine details in your image. And then your GAN needs to make all three of them happy. It's as if there are three graders for one assignment that the generator submits. One of the graders looks at the big picture. The other ones are more picky. They look at your final answer. And then GAN should make all of them happy, your generator. And then we learned about feature matching before. That's your feature matching. Try to match the features for your discriminator. And that's it. These are all of the contributions. Not only that, you also need to have a boundary map. Otherwise, all of these cars in your semantic label map are going to be having a color of blue. So every single pixel here is going to be blue. So every single pixel here is going to have a blue label. But then it matters that this is a different car from the other car. That's why you're going to include the boundary map. These are one-hot vectors. Whenever you have a boundary, it's going to be a 1. Whenever there is no boundary, it's going to be 0. And then these stuff you concatenate with your semantic map while you're doing your training and inference. And then you're going to get some high quality images and some numbers to report. Any questions about Pix2pixHD? Was everything clear? Okay, perfect.